So in the first day of the experiment, you isolated the chloroplasts. From the chloroplasts, you isolated the thylakoids. Today, you're going to have taken the thylakoids that you got, you're going to have taken the numbers that you got from the spectrophotometer, and you're going to make sure that you have diluted your thylakoids down to 1 mg per mil. Refer to the lecture on Photosystems to make sure that you understand the math of how to dilute it down to 1 mg per mil using the numbers that you got on the spectrophotometer. So after you have diluted your thylakoids down to 1 mg per mil, you now need to use Triton to separate photosystem 1 from photosystem 2. It's a very simple procedure. You're going to take your 2 mils of your 1 mg per mil solution of chlorophyll, and you're going to put it into a tube. And then you're going to calculate how much of the 25% Triton you need. And again, refer to the lecture for those calculations. So how much of the 25% Triton do you need to add to 2 milliliters of 1 mg per mil chlorophyll? And the answer in this case is 20 microliters of Triton. So I have a P20 set to 20 microliters. When you are taking your Triton, it looks like almost like a watery solution, but it's actually quite viscous. So when you are taking samples out of your Triton solution, don't put the pipette all the way into the top of the pipette tip. Make sure you're only putting the tip of the pipette in, otherwise you'll have excess Triton running down the outside of your tip. So you're just using it in the top of the solution just to get 20 microliters out. When you have 20 microliters out, you're going to add that to your 1 mg per mil solution, and you're going to mix. You're not going to vortex or anything like that. You just want to make sure you mix. You want to avoid a locally high concentration of the Triton. And then you're going to put it on ice for 30 minutes to allow the reaction to proceed, to allow the photosystem 1 to separate from the photosystem 2. Okay, so now we're going to learn how to pour our gradient. We're going to be pouring a gradient that goes from 15% at the top to 50% at the bottom. So this means the first drop in our tube needs to be 50%. To make this happen, we're going to take 50% sucrose. Now, before you add it to your gradient maker, make sure that all of your connectors are closed so it doesn't leak out and go someplace that you don't want it to go. So we're going to start by adding. I know the protocol says 15 mils, but we're going to do a little extra. We're just going to do 17 mils. Of 50% in the side that's closest to the outlet, so that the first drop that comes out will be 50% sucrose. So then after you have added it to the side that's closest to the outlet, only then can you open the connector between the two sides a little bit. And you want to open the connector between the two sides, because otherwise if you put 50% in here and 15% in here without opening it, there will be an air bubble in between, and that air bubble will never go away easily. So you open it just a little bit to let a little bit, just 1 drop of the 50% flow back into the other side, and that gets rid of the air bubble. If you make a mistake and accidentally open it for too long, you can always take the 50% out here and put it back in your original side. So now we're going to put 17 mils of the 15% in the other side. So now you have both of your solutions in. Before you start to pour your gradient, remember to open that connector between the two. Otherwise, all you will have is 50% sucrose and it won't be a gradient. Now, we also have a little stir bar right here. So by turning on the stir plate, this starts spinning our stir bar. And the reason you want to make sure that you have your stir bar going is as you take the 50% out from this side right here, some of the 15% is going to come into the 50%. And you want to make sure that that's adequately mixing so that you are getting 50% and 49 and 48 and a little bit less all the way up to 15. So notice we have tubing here that is connected and it's still closed. Notice we have tubing here that's going to go into our tube. So we want to make gravity work for us, which means we want the tube to be below the level of the counter, definitely below the level of the solution in here. One mistake that students very often make is they'll have the tubing, up here, and they'll say, well, my tube outlet is below, but if your tubing is higher than the level of your solution's not going to flow down the tubing. So you want everything to be a nice smooth slope down to the bottom of your tube. Now, you don't want to add it too fast. To make this gradient, to have both of these solutions come out, should take at least 5 minutes. If it's taking less than 5 minutes to pour your gradient, you are doing it too fast. And you can adjust the rate of flow by opening and closing this spigot a little bit. So you can have the solution flow a little faster if it was open more, or a little slower by closing it down more. So I'm going to close it down a little bit more. So I'm going to have it flow a little bit. It's easier with two people, having a lab partner, to adjust the flow. So as my 50% is coming down here, my 15 is coming in here and getting stirred around. Okay, so notice now I have some solution flowing into the bottom of this gradient. Now what I'm doing is I'm not holding it in the middle, I'm not allowing it to plunk down in here, because allowing it to plunk down is going to destroy the gradient. I don't know whether you can see that.
Yes.
Okay. Okay.
Actually, the darn picture really helps.
Okay. So you want it to flow very, very slowly in here. And if it flows too fast, you will not get a good gradient. And if you start plunking it down in the middle, you will not get a good gradient. So you want just a slow flow down the side of your tube, preferably with your tube as vertical as possible. So letting that happen. So it's going to happen over a 5-minute period of time. We're just going to let it flow. As the solution starts to get lower in here, your lab partner may want to help this out by turning this over to the side or lifting it up and helping some of this come out. But make sure that the stir bar keeps going. And if you were to, when you do this in person, if you were to look at this closely, you'll see the little lines of mixing. So it's kind of hard to see, but with the two different solutions coming in there, you can see how the stir bar is allowing those two different concentrations of solutions to mix. Okay, there we have 2 gradients. And we have a little bit. So now that the thylakoids have been treated with the Triton X100 and allowed to dissociate photosystem 1 from photosystem 2, which is still integral in the membrane, you're going to load them and do a rate zonal centrifugation in an ultracentrifuge, because that is where our rotor is. So to do this, you're going to take 1 mil of your untreated sample and you're going to layer it on one of your gradients. So to layer, you're not going to inject it. You're going to very carefully lay it over the surface, very carefully and very slowly, so it just flows right across the surface of your gradient. So it looks like this. And you're going to do the same thing for your treated sample. This is your sample that has been treated with Triton X100 for 30 minutes. You're also going to take the same amount, 1 mil of that, and layer it across your gradient. Just like that. And now you're ready to spin them. So here we are with our sample and a swinging bucket rotor. A swinging bucket rotor is one of the other types of centrifuge rotors that you can use with either an ultracentrifuge or a super speed centrifuge. So to use a swinging bucket rotor, generally they have numbers on the top here. So this will be number 5, number 4, number 6, etc. And those numbers go with the little buckets. So this is number 4. So the 4 cap goes with the 4 on the bottom. And because these are made to go in an ultracentrifuge, they're made to go very, very fast. You don't ever want to mix up. You don't want to put cap number 3, for example, on bottom number 4, because then they will not be balanced across from each other properly. So all of these buckets are made to weigh exactly the same thing to a very, very high degree of accuracy, so that you can spin them very fast if you need to in an ultracentrifuge. So in a swinging bucket rotor like this, there's a bar here, and underneath here there are 2 little hooks, and the bar just goes over those 2 little hooks. So basically, here's the hooks that are underneath here. Here's the bar, and you're going to take this and you're going to go up and over, and it's going to hook onto the little hooks, and that's going to support it so that while it's running, it can be in this position outwards. So here we are hooking it in here. Give it a little test just to make sure it's hooked properly. And so now we have our samples in number 1 and number 4. And now we're going to open the centrifuge. Now notice the center spindle in there is a different shape. Remember that earlier in the experiment, we saw that we had sort of a cone-shaped center spindle for the rotors that would be used in a super speed centrifuge. So any rotor that's designed for use in an ultracentrifuge cannot be used in a super speed centrifuge unless it has the proper type of bottom on it. So in this case, you're putting it in. Notice a very, very tiny base down there. So you're putting it in. You're giving it a little test spin to make sure it's seated properly. And then closing the door. So in this case, we're setting it to run at 12,000 RPM for 7 minutes. You can always run it longer, but you can't unrun your centrifuge sample. So if we decide we need to, we can always do longer than 7 minutes. So we are setting our speed to 12,000 RPM. We're setting our time to 7 minutes, and we're going to start. And so it's going to spin. Initially, it's going to go down to 750 microns in the vacuum. And because this is an ultracentrifuge, it pulls a vacuum. It's meant to go faster than 20,000 RPM. But if you have a centrifuge that's going that fast, you have air molecules in there, and the rotor, as it's spinning around, can hit the air molecules, causing, and the friction causes the sample to heat up. You don't want, if you have proteins or anything like that in there, you don't want it to heat up. So an ultracentrifuge pulls a vacuum as part of its process. Now, as a safety measure, so it doesn't go, if you have it set to 80,000 RPM, for example, if you have a rotor that can go 80,000 RPM, you don't want it to be going 80,000 RPM until you have all the air molecules pulled out of there. So how it works is there's a safety setting at 3,000 RPM. So it will stick at 3,000 RPM until it gets down to 750 microns. After the level of vacuum in there is down to 750 microns, then it will go up to your running speed, and it will run at your running speed for the remainder of the time, and it will come down. And so if you wanted to right now, there's a vacuum in there. You couldn't just open the lid, even despite the safety interlock that's in there, but you'd have to release the vacuum first because it is pulling the vacuum. So it's going to go up to 12,000 RPM, come back down, and as it drops below 3,000 RPM, then you will be able to push the vacuum button to release the vacuum. And only after you release the vacuum will you be able to open the lid. So that's a common mistake that people make. They forget to push the vacuum button to release the vacuum, and they're pulling and they're tugging and they can't open it, and they don't know why it won't open for them. That's because they have not yet released the vacuum on. So basically, we're going to stop the video now, but rest assured it will go up to 12,000 RPM as soon as the vacuum is complete. You can see it starting to go up right now. It will go up to 12,000 RPM for the remainder of the spin, come down, and we will next show you what the samples look like at the end. So on the left side, you see our untreated sample, and the untreated sample has nothing up at the top because our photosystem 1 is still attached to the photosystem 2 and the membrane. Further down in the tube, you can see the band where you have the photosystem 1, the photosystem 2, and the membrane. On the other hand, in our treated tube, we have up at the top a green band, and that's because the photosystem 1 has come apart now due to the action of the Triton away from the photosystem 2 and the membrane. And we can still see the photosystem 2 and the membrane further down in the tube. So why do they separate? Well, remember, they're different sizes. And when we're doing a rate zonal centrifugation, it is still separating on the basis of size, using a density gradient for stability, but separating on the basis of size. So something that is an intact membrane with the photosystem 2 is a much larger size than just the number of proteins, I think around 17 proteins that make up photosystem 1 that have come apart and away from the photosystem 2 and the membrane. And so those are appearing now at the top of the gradient because they are so much smaller in size.